Okay, so did anybody actually put any thought into this bell ringer question? Yeah?
I said it would be the catcher because they didn't have enough force to stop the ball.
So why is the force of the catcher greater than the force of the pitcher? Because here's my logic. Okay, let me paint a picture for you. The pitcher has to accelerate the ball from like say 0 to 98 miles an hour, right? The catcher has to accelerate the ball from 98 to 0. So we have the same change in velocity. You get what I'm saying? So then my question is, if they're making the same ball, change the same amount of velocity, which one is going to exert a greater force? Does that make sense, Timber? You sticking with that answer? I'm not telling you you're wrong, by the way. I'm just like making sure everybody understands it, because I should have explained that before I took responses. Does that make any sense? Okay. Does anybody else want to offer an answer? So Timber is sticking with the catcher, right?
Okay.
Is that what you said?
No.
No? What did you say?
That I wasn't going to stick with the catcher.
Oh, you're not sticking with the catcher.
No.
Okay.
Now I don't have an answer.
Okay. All right. Who else?
I think I would stick with the catcher too, just because that's the stopping force. So I feel like it's going from like 100 to 0 a lot faster than it's going from 0 to 100.
Okay. So you can pinpoint something that's different about the two, right? Mm-hmm. That's critical. So the pitcher takes more time to accelerate the ball than the catcher does. Does that make sense? So what impact does that time period play?
Acceleration.
Sure. Yeah, I mean, if I can do it for a longer time, then I actually can have less acceleration, and that should equate to less force. You follow? So that's the right answer. The catcher was the right answer. So the catcher is more force. Now, we can common sense our way through this, but what we're going to show you here in a minute is that there's actually a nice mathematical statement that will help us with this. So if you and I say common sense, you're physicsing through it, right? So we can do that with the following line of reasoning. So I could start by saying, well, they both have the same change in velocity, right? But the catcher is going to do it in far less time, right? Because like if you ever watched a baseball game, you would see that the pitcher like takes the ball and does this whole like elaborate wind up and throw, right? And even if you just narrow it down to the throw bit, it takes some time. Like you can watch it happen, but if you watch the catcher catch the ball, it's essentially instantaneous, right? Like it hits their mitt, it's done. You can't see it slowing down in the mitt. You get what I'm saying? So that must be a much shorter time. And if I have a shorter time, that means I must have a greater acceleration. And if I have a greater acceleration, that means I must have a greater net force. Does that make sense? So I can go through kind of that line of reasoning. Now, it'd be really nice if we had some sort of a mathematical equation that would actually help us to get from point A to point B a whole lot faster. And that's what we're here to talk about today, is impulse. So impulse is going to relate force, time, and changes in momentum. This is also, I think, one of the most easily applicable ideas in physics that will help you to, understand the world around you a lot better. Because basically, it sets up this relationship that we've seen here. That given a certain change in momentum, if I can make that change happen slower, then I can decrease the force on the object. And it turns out that simple concept is extremely helpful for keeping people from dying. So it's like a really good thing. So let's hop into it. So I'm not actually going to derive impulse for you. You can get it out of Newton's second law, but I'm trying to keep this down to just the important bits. So let me actually just say that this comes from Newton's second law. That's where it's derived from. Normally I like to derive all the things for you, but I'm trying to be brief here so that, I don't waste a little bit of, what's the word? No. Give a crap that you all have left, right? I want to make sure I use it well, because I know it's quickly fading. So we're just going to get straight to it. If you're interested in the derivation, come talk to me later. I'll show you. You don't need to know it. But what I get is this equation here. F delta t is equal to m delta v. Now, Sometimes you'll hear me refer to this as the fat math equation because it kind of looks like it says fat math. But what this is relating is force, time, and momentum. And that's an extremely useful thing, right? So like when we saw the work energy theorem, that was like the net work is equal to the change in kinetic energy. And I was like, hey, this is like super cool, very useful thing, right? This is on the same level of like super cool, very useful, help you solve a lot of problems a lot quicker, okay? But it's just a simple equation. That's all it is. We're going to talk about a little bit of application with it, but it's really just a simple equation. You need to know how to use it. That's it. Does that make sense?
Mm-hmm.
Okay. So going back to this, we should be able to see why, using that equation, a really simple relationship. So if I say F delta T is equal to M delta V, we agreed that they both have the same change in velocity, right? Or at least the same magnitude of change in velocity. So we should agree that both the pitcher and the catcher, this is the same, right? They have the same change in momentum. By the way, I didn't say this explicitly. Remember that momentum is equal to mass times velocity, right? So then a change in momentum would be equal to mass times a change in velocity if we assume that the mass stays constant, which is typically a safe assumption. That's why I'm calling this change in momentum. Does that make sense? Didn't explicitly say that. So we're saying F delta T is equal to the change in momentum, and that, at least the magnitude of it, is the same in both cases, right? So that means that any difference in force is going to come down to a difference in time. And that's where Michaela's argument is a very good one. Because I can then come back and say, yep, the catcher is going to be catching the ball for an instant, whereas the pitcher is going to be taking a little bit of time to actually accelerate the ball. And now I don't have to jump through the Newton's second law hoops. I can just see it right there, right? Like I can just say, same change in momentum, different times, different forces. That's it. Does that make sense? It's a nice equation that links some things together. That makes our lives easier. Cool. All right. There are some examples here of just using the equation. I'm not going to do that because it's just an equation. But this is the bit that I think is actually useful to you. I want to take this concept and try to apply it to things like collisions, because I think that's where you see why this is like extremely useful and something that you should care about just as like a human. Because I think it'll help you to make better choices as a consumer, and better choices as a driver, and better choices as just like an adult. So I have a question here. A large truck and a Prius collide. Which car experiences the greater force? So the truck or the Prius? Y'all want a minute to think about it before you just jump in there, or do you feel really confident here?
The truck.
Okay, so I guess I got a truck,
Prius.
the Prius. Anybody else?
Didn't we talk about this before? We talked about how it was school.
We did. Newton's third law would say this is equal, right? Two things colliding is an interaction, and that's why we have Newton's third law, is to answer these kinds of questions for us, to tell me if the truck and the Prius collide, they're going to have the same, sorry, that sneeze threw me off, not your fault, it just got me. They're going to have the same force on each other, right? Does that make sense? Okay. So then which experiences the greater change in momentum?
Wouldn't that
Tell me why.
because the truck it has like more force behind it, and so when it collides, then the truck is maybe gonna go like, but the Prius is going to go like, boom.
So I agree their change in velocity will be the same, but that doesn't necessarily mean their change in momentum is not the same. Maybe we should apply this equation here. If I try to apply this equation, we just said this F is the same. Over here is change in momentum, right? So what can I tell about the time over which that force is acting? How do those compare? Because if F is the same, the only way those are different is if they interact for different amounts of time, right? So do they? No, it'd be nonsensical to say the two cars that collide with each other collide for different amounts of time, right? Does that make sense? So what this tells me is that in any collision, the two vehicles, the two things, whatever they are, they will always have the same change in momentum. Now, to go back to your point, the truck is more massive, right? So it'll have a smaller change in velocity. But the change in momentum is the same. So this is the important thing you need from taking impulse and combining it with Newton's third law, is because this is like how the universe works type stuff. Like, this is really important to understand. The way the universe works is that anytime two objects interact, they experience equal and opposite changes in momentum. Okay? If we get a chance to watch Interstellar, there's a really good line in it towards the end. How many of you guys have seen it? Okay. So towards the end of the movie, TARS, who's this like robot, is talking about Newton's third law, right? And he says, there's a dramatic thing happening, and somebody's like, no, why is this happening? And they're like, hey, it's Newton's third law. You have to leave something behind. I'm getting chills. It's a really good moment in the movie. Anyways, that's like an actual thing, right? Like, the only way you can ever move is by moving something else in the opposite direction. So literally, the only way you can ever move forward is by leaving something behind, which is just like important to understand about how the world works, but also it's a nice life lesson, right?
Are you tearing
I
up?
know.
No, not right this moment, but if we watch that movie, I will cry, because I love that movie. It makes me cry. But point being, that's like an important principle of the universe, right? The only way your momentum can change is if you interact with something else and change its momentum in the opposite way. Now, this is a fact of the universe that's not really apparent to us because we live on the earth.
Teachers, as we go to Stop the Bleed today, please be prepared to mark a list of students to let us know who is absent from the training. We are ready for 8th grade. Teachers, if you are ready, you may go ahead and bring your 8th graders, and be sure to stay with them, please.
Okay, so this is an important fact of the universe that we don't know because we always, like, the bulk of our interactions are with the earth. So we don't really see that opposite momentum change, right? But if you're going to start considering things like interstellar travel, that's really important to understand, right? The only way I can change my momentum is to change the momentum of something else. In fact, that's how like rockets work that we use to travel through space. Is basically the concept is that if I can blow stuff up and push hot gas that way, then it'll push my rocket that way, right? And then there's all sorts of issues with doing that for like long-term travel that we don't have time to get into. But that is an important principle of the universe. Does that make sense? Okay. I just talked about the rocket, so we'll be done with that, right? Which, by the way, I think that's important because like there's a lot of bad physics in movies and books and all sorts of stuff. Like, I love Star Wars. The physics in Star Wars is just awful. It's like they just pretend it doesn't exist. It's like whatever, but it's fine because it's fun. Until they made Episode 9 and ruined everything. So, anyways, let me get on a soapbox about another issue that I think is important for you to understand. I'm gonna try and keep this brief because I want to cover those other two topics. So here's the deal. At some point, like right now, you probably have like whatever car your parents got for you, and you're just kind of like locked into that, right? And you just gotta hope your parents are smart enough not to give you a death machine. Like that's just like the world you live in, right? Which is fine. But at some point, you are going to have to go buy your own vehicles. And I think this is a great moment to talk about what kind of cars you should buy from a safety perspective. And it all comes down to this idea, because if you're an engineer and you're designing a car, what you can't change is the change in momentum somebody in that car is going to experience, right? Like you can't stop that. People are going to go be stupid. They're going to drive at 65 miles an hour without paying attention and run into somebody. It's just a thing that happens, right? Can't stop that. But what I can do is if I want the passenger to experience less force and therefore be less likely to die, I can control this time thing here, right? So the reason modern cars are built the way that they are is because a lot of engineering goes into how can I make this time of impact as large as possible so that I can decrease the force on the human that's inside this tin can. Does that make sense? So that means that a lot of cars have what we call crumple zones, right? So if you've got like an old boomer uncle or grandfather that's like, nah, cars these days, they just blow up when you get in an accident. They're right, but you didn't die, and that's kind of the point, right? Like the point is we designed the car to have kind of like a strong place so that you don't get crushed, but then for everything else to be crushable, because as that thing is crushing, it's taking up time, and that's making the force on your body less. Right? It's making the car safer. Like there was this thing, like God bless Ford, because they should have known their consumers are morons. They put out the F-150 like probably 5 or 6 years ago. They went to these like all aluminum bodies, and you had like dumb rednecks that were like, look, I can cut my car open with a pocket knife. And it's like, yes, they made that part weaker on purpose so that your dumb ass would not die. Right? Like you need to understand. Oh, camera. You need to understand that this is important, right? Like, I don't want you to go be the idiot. Like, I want you to understand that this is how cars are designed for a reason. Does that make sense? Like, there are parts that are supposed to crumple, and that's a good thing. Yeah.
Which part could they cut open?
Like the doors.
Come
Yeah.
on, Caitlin.
So here's the deal. One, understand that like engineers are smart people. If they choose to make the car out of aluminum, it's probably because it offers an advantage in several areas, and they decided to do that. Okay, now here's the deal. Listen. I know we live in West Texas, and trucks are cool, right?
No, they don't.
But I want to very quickly, because this is the last thing I'm going to talk about, and we're going to move on. I want to very quickly tell you why they are a poor choice unless you actually need a truck. The same thing goes for big SUVs, okay? The reason these are bad choices is because they're much harder to engineer to be safe. Okay? I'm going to design 2 cars for you really quickly on the board. Car A is going to have a very strong passenger compartment because every car needs that, right? I need a passenger compartment that's not going to crumple so that I don't squish the jelly bags inside, right?
Jelly bags.
Yeah, you. So car B is going to have that same region, right? Like the passenger compartment needs to be strong, so I'm going to start with that building block for both of them, okay? Now, for car A, let's say this is like a minivan or a sedan or any sort of like smaller car. Well, I don't need to make the rest of this very strong because it just exists to haul people around, right? So all it needs then is for me to put a shell around it that all of this shell is now crumpleable, right? Like all of that I can squish and it's okay. Like it might totally mess up your motor and all that, but that's fine because I'm trying to keep people alive. Now instead, let's say you have either a large SUV, which is really long and heavy, or you have a truck that's designed to be like hauling heavy things. Well now, because it's big and heavy and needs to do big heavy things, I can't design it where the rest of this is all pretty weak. So instead what I have to do is I have to create a frame. So this is how they used to build all the cars until they realized it was very unsafe, and now they don't do it anymore. So now they use something called unibody construction, but these other trucks, they use what is called a frame-on-body construction. So they take this body and they put a frame on it, which is just like really strong steel, like so, right? And now this car is so long and so strong that when I build on these crumple zones, what you see is that there is very little crumple. Because now this has very little like vertical crumple. The side is still fairly crumpleable, right? I didn't change that a whole lot. But the vertical crumple is almost nothing. So what does that mean for when this car full of jelly bags runs into a brick wall? It can't crumple, the time period is really small, and so the force is really large, right? That's why if you look at crash test data, trucks are the most unsafe vehicles on the car, or on the road. So, your parents don't understand physics. Some of them do, right? Like I bet your dad knows this. He's a smart fella. So your parents don't understand physics, and so they have this moronic misunderstanding that the bigger car is safer, and it's not. It is in fact more dangerous, and I don't have time to explain it all, but it's actually not just making it more unsafe for you, it's making it more unsafe for every other driver on the road, right? So here's your lesson, okay? Trucks and SUVs are cool in the fad, but they're gonna kill you. So like, go buy a sedan if that's all you need, because it's safer.
A Prius.
Does that make sense? So that's my thought. That's actually that's why I bought a Prius. That and because I'm a hippie. Okay. Do you guys have any questions about this? Yeah.
Just a brief question. Does this change for like electric cars? Any like the thing?
Not really, because electric cars make a space trading between the engine block and the battery space, and so it's about the same. It doesn't really work out one way or the other. Electric cars have a minor safety hazard in that when they get into accidents, there's a higher risk of fire and there's a higher risk of just like electric shock.
Oh, good.
Not considerably though. You know, like again, we're talking about like electric car has high voltage versus gasoline car is filled with combustible material, right? So like there's a minor greater risk, I believe, with electric cars, but I may be wrong about that. All right, anything else?
We need to make a different video.
I was gonna say.
Thank you.
Video.
Okay, life lesson of the day: don't buy a truck unless you need one.
Oh.
Okay.